Okay, welcome back. Now let's move on. Uh, the next topic, actually, Taylor series representation. So far, we actually see how to represent given function by using very well-known Maclaurin series. Actually, we can do this kind of trick for Taylor series. Remember, for Taylor series, we actually have different center of um, expansion. So the center of expansion is a little bit different, right? So, but actually, the main idea is um, actually we can change everything back to the case when Maclaurin series are available. So what I mean is that main idea here or our strategy is change of parameter. And then the second step, so this is our first step. The second step, use Maclaurin series. Okay, maybe I should try to tell more clearly. So where is it? Okay, so this is our strategy basically. So let's try to apply this idea. Here, if you look at carefully, so our center is 1, center of expansion. But actually, we can really see center of expansion like this. And why don't we use a new coordinate, t, and try to expand everything around 0? Meaning, why don't we study Maclaurin series after change of parameter? So let x minus 1 be t. Then, of course, then we should observe that of course, our function, we use the change of parameter for the given function. So actually, we have 1 over 2 plus x, but this can be rewritten like this, right? 3 plus x minus 1, right? Therefore, this is just 1 over 3 plus t with our new coordinate system. But let us manipulate it in one more step. And this is exactly, if you take the parenthesis of 1 over 3, so we have something like this, right? So can you follow? So actually here we recall the following. So just recall that this light, so this looks familiar, right? So just use our famous Maclaurin series. So what was it? Which is this, and starting from 0, t to the n. So this is the case if t is less than 1. So if you use this, as you see, so we start with this one, we somehow end up with this 1 plus t divided by 3. But if you look at carefully, now we can use and actually enhance, remember, 1 over 1 plus t is just something like this, minus 1 to the n, t to the n, t with this interval. And let's use it. So let's use it with, instead of t, we have, so we just replace, so use this, right? Use this information. Let me call it star. So use star, but with t plus 3 instead of t. Okay? So we did this before. We know how to use or manipulate the given series, right? And so this is more or less, this is what it is. So let's do this trick. So we have this term here. Okay, maybe. So what is it? So we have, okay, we have this. Okay, n starts from 0, minus 1 to the n. Instead of t, we have t over 3. So we have, 3 n here, right? Am I correct? I guess so. But now instead we have t less than 3, right? Because, instead of t, we replace by t to the 3. And this thing turns out to be this restriction, of course. So no problem. But remember, what is t? So we just introduce t, right? We just invent t somehow to use the Maclaurin series representation, right? Therefore, just resubstitute back. So just resubstitute, resubstitute. Remember, x was, so what was it? X is 1 plus t, or whatever. T is x minus 1. And therefore, we have this. Minus 1 to the n divided by 3 to the n. So instead of t, we just resubstitute everything. Aha, this is exactly what we want. So this less than 3. Of course, we should manipulate this one. So this part actually, maybe we should be careful. This is exactly, so let me write it down. Right, something like this. So add 1, x, and 4. Okay, so fine. So what we have at the end of the day, so we get the following Taylor series representation. So we get the following: 1 over 2 plus x has the following Taylor series representation, and around x0 equals 1. So this is the case. If this was around x equals 0, this is the Maclaurin series, right? But so what's happening? Oh, what's going on? Is this serious? Okay, I will correct this. Okay, in the notes I will correct this. Anyway, so somehow at the end of the day we have, so what we get, I mean, 3 to the n, x minus 1 to the n, and starting from 0, but we have this kind of domain of convergence. Okay, so but this is not done yet. So we have one more job. Basically, remember, we should be careful about this, right? So we should be careful. But remember, we don't do any integration or differentiations, and basically we have the result. Okay, so we don't need to check endpoints, but in the next problem we should be checking the endpoints. Okay, fine. So that's all. This is basically, I guess, if okay, you should be careful. Okay, so that's maybe I should. Okay, why don't we? Okay, I see. Just get rid of this part, maybe in a more compact way. Plus, oops. Plus 1. And we are done. So what about part B? So for part B, so what's, I don't know what's going Okay, fine. So part B, so the similar trick here. So the similar trick. So we have, of course, this is what this equality tells us. And similar idea, we just change the parameter and we use Maclaurin series. Okay, so let's do this. Should be, okay, so let's see what we have. So, okay, so for part B, we just let x minus 2, right, to be t. So with this change of parameter, then we get the following. Of course, we should write it down, everything in the language of t. So we start with this function. So now in this new coordinates, t, this is just logarithm. So instead of t, we have 4. So instead of x, we have t plus 2. So we have 4 plus t. And actually, we can still have things to do, just to take the parentheses of 4, for instance, 1 t to the 4, right? Something like this. Use the properties of logarithm. We have ln 4 plus, okay, ln 1 plus t to the 4. Okay? And now we should be careful. So we should recall our previous problem. We should recall, actually, if you like, question 2, part A. Just recall that. Actually, we did this. Recall that logarithm 1 plus, let me use new parameter, or let me use directly t. Okay, 1 plus t. What was it? So let me write it down. Minus 1 to the n, t to the n plus 1, I guess, and something like this, n plus 1. What? We should be careful with this. This is not true. Remember, we checked the endpoints because we did a kind of a term-by-term integration. This was the domain of convergence. So we did this. Okay, since we did this, let's try to use this idea. I mean, this representation, but in place of t, we will have t over 4. So let's do this. Then just observe. Okay, what we observe, so logarithm, so what we are looking for, 2 plus x, is just, okay, this is what we have after change of parameter, 1 plus t over 4, and just use this recall, right? Use recall, right, with t to the 4, right, instead of t. So let's use it. So that there is nothing changed here. Plus, now we have a kind of a series representation. Okay, minus 1. Why are these are disappearing? Okay, I don't know. I don't really know. Okay, fine. And something like this, t to the n plus 1, and divided by, so instead of t, we have t over 4. So something like this times n plus 1. Okay, I guess this is the case. But of course, with minus 1 t divided by 4, 1. Or if you like, minus 4 t 4. Okay, with this range, with this domain of convergence, we have this equality. Otherwise, this equality is not true. Always, you need to specify the domain of convergence. Otherwise, these equalities are not true. And fine, of course, we just invented t, just go back. So t was x minus 2, I guess. And with this substitution, we have logarithm 4. Everything is fine. Now we have n starting from 0. We have this and this term. Okay, fine. But instead of t, we have x minus 2 to the n plus 1. And if you replace t by x minus 2, your domain of convergence will be minus 2, x, and 6. Right? And this is basically what it is. I mean, this is exactly your domain of convergence. And we are done, actually. This is your result. Okay? Therefore, to sum up, so therefore, logarithm 2 plus x is just its Taylor series representation will be this, and starting from 0, minus 1 to the n, 4 to the n plus 1. You see the center of the expansion is 2, right? N plus 1, but of course with this radius, I mean with this domain of convergence, okay? And we are done. As I said, so we should be careful, but as you see, dealing with Taylor series, okay, is not that much hard, right? If you know Maclaurin series, we just change the parameter, and so that actually everything turns out to be the usual setup for which we can use Maclaurin series. Therefore, we just simplify the cases by using change of parameters, okay? And then we use the usual ideas from Maclaurin series by introducing new parameter, but of course we should resubstitute back everything because we are looking for a kind of a Taylor series expansion about some point, right? Not 0. If it was 0, it's just a Maclaurin series representation. But as you see, we just change the coordinates. In this new coordinate system, it's enough to use Maclaurin series, and then we rechange the coordinate system to the original one, and then the Maclaurin series become, basically, it becomes what we need. Fine, so finally exercises. By using the same ideas, you can really, I mean, these are not good exercises. By using the same ideas, you can actually compute, write it down, the Maclaurin series for those given function in the first problem. And in the second problem, even if it says Taylor series, by using the change of parameter, actually you can, I mean, the question really turns out to be a question about Maclaurin series, okay, by using suitable change of parameters. Actually, in this new coordinate system, it's enough to find the Maclaurin series. Therefore, dealing with Taylor series type problems, actually, by using suitable change of coordinates, boils down to the problem about Maclaurin series, finding Maclaurin series. Okay, so that's all. Thank you very much, and see you next time.